And let's look how the session is organized. I'm going to go through just a few slides to tell you what is going to happen. And we have 3 exercises, as usual, 3 blocks, where the first one is an introductory exercise, getting you warm, getting you used to using Matlab intuitively, interactively, and feeling that it's actually a very nice toy of your research. Whatever you are doing, basically, you can also do it in Matlab. We're then doing an example which is not in the materials, but which is particularly directed to people who have a problem with the kind of abstraction that's around when you're dealing with Petri nets. We understand that for some people it's quite a big gap from biochemical or biological thinking about interactions into this very formal treatment in terms of input and output matrices and looking into null spaces. These are all sort of strange concepts from outer space if you have a biological background. So we try to make that more intuitive. So the single reaction thing is a very simple thing, but it's not saying anything different than from what is in the material. We can then look at the gene expression example, which is in the materials, and just derive it point by point, live and in front of you. That will end the session if we have a few answers. I haven't mentioned this, so I go back to this. If we have some questions during the session, at the bottom of the tray of the control panel, there's the chat functionality where you can see messages that Rob is typing currently. If you type something in there, either Rob or myself can pick it up. And we don't promise we can answer everything live, but we might refer it for later. But if it's something that we can attend to immediately, please type in a question. And if we have a few minutes time, we'll look at it later. All right, let's get going. And you have seen us both here in the studio. For the rest of the exercises, I'm going to switch the camera off to have a bit more power for our Matlab slides. So we've said that we're trying to look at matrices as a warm-up. The corresponding code file is called matrix code, and you can download it if you want to do look at things later. So the experimental model, if you care to look up for it, is shown here, plasmid replication, where people have actually measured the number of plasmids in bacteria over time, how it increases, and I found a way to actually stimulate the doubling or the production of plasmids, so to increase this number in a very good way, in an exponential way, such that very large numbers, copy numbers, could be predicted. And that was the basis for what later Brendel and Perelson, then using network approach, basically formalized and took it all the way down to derive a quantitative model. First, look at the network interactions, shown here on the left side, and on the right side, what we're not going to do today, to actually derive a differential equation, which is then what you're going to learn in the upcoming sessions of SysMIC course number 1. So, exercise consists of dealing with this matrix formalism in 2 specific examples. So we're not going to do these examples, but something very closely related. And we are going to start by pointing you to one of the files that you can download. Is actually a summary of all the definitions that are in the materials, because we are conscious that they are very much distributed. So if you download these files, it's all from the materials that you can find online, but it actually brings them all together, all the definitions that you need when you want to look at what is an input matrix, what is an output matrix, what is a reaction matrix, and so on. And also there's a picture of Carl Petri, a German informatician who designed this whole formalism. So please take a look at this file to download if you want to do it. And we're going to start with after the matrix exercise with this reaction. So let's go to the matrix exercise, and Rob is going to help you do it using Matlab.
Hello everyone. So we're interested in building some matrices and reminding ourselves how the ways we can set and manipulate different values within them. I think one thing that we didn't cover last time, but that we're going to now is one easy way of getting an example matrix. So for instance, we're not actually really worried what the numbers are, we just want a matrix that we can play around with. Well, Matlab gives us this function called rand, short for random. Now we need to give this a size of the matrix. For instance, if we say 3, it's going to give us a 3 by 3 matrix. And so you can see here the random numbers are all between 0 and 1. And that's the default, and you should always expect numbers between 0 and 1 given the rand function. But actually we want to store this. So again, my matrix equals rand. And I'm going to say we want a matrix of size 5 by 5. Okay? So if I expand this out, then we should be able to have it all on one row. So I'm going to make a new matrix. There we go. So there's a 5 by 5 matrix filled with numbers between 0 and 1. And do you remember what happens if we want to change one element to 0? Say we want to change the second row and the third column to 0. I hope that's the right way around. My matrix. My matrix, and then circular brackets, so 2, 3 is equal to 0. And so you can see the second row and the third column is now 0. But what happens if we want to change all of, say, the diagonal elements to 1? Well, the first thing we could do is do this using a loop. For instance, if we type 4, so I is going to be our iterator, so that's going to store the value of the current row and column in this case, from 1 to the size of the matrix. Now we don't know. We do know that's 5. We could find other ways of finding that out as well. Okay, so now MATLAB knows that we're inside this loop and hasn't automatically done anything. So actually, we want to then do my matrix. And I, to say the ith row and the ith column, and we want to make that, say, equal to 1. We don't want to know what it's doing. And then MATLAB needs us to type the word end in before it knows to finish this loop. Okay, because we put the semicolons on there, my matrix wasn't returned, so let's have a look what it looks like by just typing my matrix in. So I hope you can see now that all of the diagonal elements are equal to 1. But there is an easier way to do this, and this is using the diag function, diag, my matrix. And so that, if I press enter, gives us all the diagonal elements, which of course are now 1. But I think we can also type in equal to 2. Nope, we can't. I didn't know that. So you have to do that within a loop. Okay. So that's useful. What if we want to? So all the numbers there were between 0 and 1. What happens if we want to have numbers between, say, -1 and 1? Then we can get we can try playing around with how we make the matrix. So we're going to have a new matrix by matrix, and that's going to be equal to 2 times rand. We're going to give it a size 5, and then we're going to subtract 1. So what this is going to do is it's going to make a random matrix. It's going to multiply everything in that matrix by 2 and then subtract 1. And that's one way of making sure our numbers are going to be between -1 and 1. Okay, and that's given us what we expected. So we've got an example matrix like this, but we want to find all of those numbers that are larger than 0. So MATLAB has a useful function called find. So if we type find in brackets and give it my matrix, we need to tell it what we want it to compare against. So my matrix greater than 0. Close brackets. And that's given us a list of numbers. And so I'm going to pass back to Gerald at this point, who will take over the rest of this tutorial.
Okay, so first thing is when we have this list of numbers, what is this number telling us? Actually, it's telling us the position of the elements that are larger than 0. So a way to check it is to first look at the my matrix again, and then to say, aha, our search for values larger than 0 shows us that the first and the third element are larger than 0. So which one is which? So we find out by comparing that, for example, the first one, the third one, and the fourth one are positive, that it can't be telling you row-wise, because the fourth element in the first row is negative, whereas the fourth element in the first column is positive. So just by comparing, you can see that is a column-wise counting of the elements from top left to the bottom right. However, we can also get this in a notation which is different, namely which tells you both the rows and the columns, which is probably easier if you want to be thinking of rows and columns of this matrix. So one way of doing is to use a very specific output, namely in square brackets, to tell it to give you the rows and the columns at the same time. And if I expand this a little bit, you can see it gives them to you one by one. You first get the rows, and then second the columns for each of the elements found. So each points at an element that is larger than 0. And of course, this is a not very intuitive way to look at it. So now you guess what we want to see. The indices a little bit nicer, namely have them together next to each other. So we can now get them by putting them in a single column, putting them in two columns next to each other. And the indices are to read such that the first one, 1, 1, tells you first row, first column is an element which is larger than 0. Second tells you third row, first column is an element larger than 0, and so on until you arrive at 5, 5, which is the element previously called 25. So this is just a little bit to show you how this runs. We can take a look at the positions, where actually which part of the matrix is positive, and we can do that by just my matrix larger than 0. Matrix is not known because I've forgotten to underscore. So you can see the position just gives you another matrix which has the same size. Whenever there's a positive number, it gives you a 1, and a 0 if there's a non-positive number. So zeros and negative numbers are there. So it's an easy way to get an overview. And this similarly, you can also use this to then manipulate these things. For example, if you say all these things that are smaller than 0, so here's my matrix smaller than 0, can be, if you look at those elements, so I feed these values that we see in this matrix by ones and zeros, we feed them into the values of my matrix. We can manipulate them, for example, setting them all to 0. So what this has done, if you look at it carefully, and I clean the screen to have this command shown again to you, it has first checked where are all the elements that are smaller than 0, where are all the negative elements, and then taken the values of these elements to be equal to 0. Which is a very convenient way if you, for example, look for concentrations and you say concentrations cannot be negative. So in a matrix that deals with concentrations, you can make sure that all the concentrations do not get mathematically negative and get not further treated as negative numbers. You can just have them put equal to 0 with this way. Okay, so you can see that just digging into the intestines of Matlab, you find a lot of useful things that will do anything for you that have to do with matrices. So the next thing is then, how do you set up your matrix, right? Your model, your biological system is set up as a matrix, and so that's what we are going to do now. Let me bring back this slide. The example that is not in the materials is a simple reaction. So we take this from reaction kinetics, and we are looking at a specific example, which is the peroxidase reaction. Peroxidases are enzymes that consume hydrogen peroxide and other reactive oxygen species, but let's be modest now, consuming hydrogen peroxide, for example, using up as a reductive agent NADH and sort of detoxifying it, making water out of hydrogen peroxide, getting rid of the potentially harmful reactive oxygen species H2O2. We receive the oxidized species NADH by this way, and in order for the reaction to proceed, we need a little bit of acid in the form of hydrogen ions. So we have a single reaction only, so it's not really yet a network, it's just a single reaction, and we want to apply our formalism, which you have seen in the materials, to create an input matrix, create an output matrix, create the reaction matrix, create the stoichiometry matrix, and then check the resulting matrices for certain features like T invariance and P invariance. And we'll have a little bit of talk about these later. So, 5 species, hydrogen ions, hydrogen peroxide, NADH on the left side as reactants, water and NADH on the right side as products. And we specifically note that per reaction step, out of 1 molecule of hydrogen peroxide, we get 2 molecules of water, resulting on the right side of the reaction arrow. So this is the thing that we need to remember. And I'm going to clear, I meant this, clear it up. So let's get started. So what will be our input matrix? Our input matrix, maybe just to remind us, we can actually set it up with some strings. We can set up a nice array of strings where we have our, I will set it up, and for 5 species. How much do we have? 1, 2, 3, 4, 5. 5 species, and they are called successively so that we don't need to look it up all the time. H2O2 is the hydrogen peroxide. Then we have NADH. On the right side we have water, which is H2O2, and we have NAD+. So this is our species vector, so to speak, here in a set of strings. Now let's create our input vector. What will be the input vector? We have a single reaction only, so it will be only a single row. And what will be the elements? We're looking now to put in molecules that get consumed, so the reactants in a step of any step of this certain reaction. So what will it use? It will use the hydrogen ions, it will use hydrogen peroxide, and will use NADH, but it will not use H2O2 and it will not use NAD+. So this will be our input vector. Conversely, the output vector, something very similar. We create it as a vector, and the products will not be hydrogen ions, it will not be H2O2, neither will it be NADH, but it will be water. But we get 2 molecules of water, if you remember, so we get a 2 at this place, and we'll have NADH per reaction as a final entry. If we return this, you can see this is our input and our output vector, shown that 3 molecules are needed to get the reaction going, and 2 types of molecules are getting out of it, but the molecule count is actually also 3 because we get 2 water molecules. So we lose 3, but we also get 3 on the right-hand side. Now, how do we create our reaction matrix? Following the material convention, we call the reaction matrix A, and it's defined as a difference. It's the difference between the product vector and the reactant vector, so output minus input. If we do this, MATLAB will create it for you, and you can see by this subtraction you can get negative numbers for the reactants, and you will end up with positive numbers for the product. So the one go away, the one will come up. And we can immediately set up the stoichiometry matrix, and it's the same as the reaction matrix, but it's the inverse of it. So using this symbol to get the inversion, we can have the stoichiometry matrix directly, now denominated S, following the convention of the materials. Right, let's look at the change. What will the change be? It was called U in the materials, so we stick with this. Let's say we have per time unit, we get 2 materials. So how much change are we going to expect if 2 reactions take place per time unit? We assign this to the letter U. It's just a single element. 2 reactions taking place per time unit. Then we can calculate the change, if you look it up, as the product of the stoichiometry matrix for each step times this number of reactions that take place per time unit. It would be 2, but we can of course use the letter U because that's how we defined our change. So per step, per reaction time unit, we get a change of losing 2 of each of the reactants and getting 4 water molecules and 2 molecules of NAD+. We can then actually start to form our model by assuming initial conditions. For every model to run, we need to know initial conditions. The initial state vector was denominated M in the material, so we keep this here. Let's assume we have a couple of reactants, initially say 10 of each species, and we have none of the products initially. Then this is our starting condition. We end up for each species 10, 10, 10 reactants, 0, 0 products, just as an arbitrary example to have something to go with. Now, how would our model run? Our model would then run as taking the starting condition, which is called M, and adding to it the change. But we know per time unit the change is S times U. So 2 reactions taking place per time unit. So this is our formula to actually calculate or how the reaction is going on. To actually do a simulation of a step. I have a problem here, Rob. Let me see what's going on.
Your matrix, your M is a row, a vector, whereas
it should not be. Right. So what I've done wrong here, as I had, MATLAB tells me that matrix dimensions disagree, and they must agree. Why is that? Because our S matrix, as you can still see a little bit further up, is in a single column, but I have arranged my initial state vector in a single row. So that's inconsistent. So how do I change it? I replace commas with semicolons. So let me do this again. Now we have a state vector that looks like the S matrix. And I think if I just get back to this line where we have the change defined as initial state vector plus change per time unit, you can see that after a single time unit, after one round, we have 2 reactions taking place, and we end up with 10 of each of the reactants, so 2 down from 10. We end up with 2 molecules of NAD+, but with 4 molecules of water, because per time, per reaction, 2 molecules get created. So if we keep going, we can then calculate how this keeps decreasing our number. So if we have, for example, 5 time units, it would be 5 times the change going on. And this is no surprise, because if we take away 2 per time unit after 5 time units, each of the initial of 10 molecules is being consumed. Everything is being converted into product, so we end up with 20 molecules of water finally and 10 molecules of NAD+, after which no more reaction is going to take place because there's nothing to react. So that was, in a way, formalism to set up a model of our system and to actually simulate it. And while we will have, of course, more convenient ways to do in the future, you have now seen how you can get a quantitative description of your system using the Petri Net formalism. Another thing that we are going to do is, if I clear this window, we look at some invariant features. And it was suggested to use this command null, and maybe we have a little bit of discussion about this shortly. But to just show you that we can, of course, apply this also to this very primitive reaction. If you remember from the materials, if you take the null space of the reaction matrix A, then, actually adding this option R to get only the real valued outputs of this, then we get what is called the P invariance. And the P invariance was meant to show us what combination of molecules remains unchanged under this reaction going on. So if we look at it, we get some output, and this is an interesting output because what we get is 4 columns. And so the way to interpret this is best done if we look at our species vector. Namely, we have our 4 species, and we can maybe do this, look at it the other way around. No, sorry, it's this way around. And I'll take a look at it again. This is what we need to see. Our species are organized in a column. So the output of the null function now tells us that what is preserved here is certain combinations of numbers of molecules. For example, if you look at the first column, you can see that it tells you that taking the negative of the number of hydrogen ions and the positive of the number of hydrogen peroxide, that this number remains unchanged. It is a P invariant. It means this number doesn't change under the reaction. So if you think of it, it's natural, because if we start at 10-10, and if the reaction goes on, we end up with 9-9, if one reaction goes on. But the difference, 9 minus 9, will be 0, which is the same as 10 minus 10, which is 0, and which will be the same as 8 minus 8 if we have 2 reactions happening. So this goes for all combinations of reactants. If we look at products, you can see that 2 times the number of hydrogen ions in the third column, combined with the number of water molecules, adding them both up. So the number of hydrogen ions times 2 plus the number of water molecules is also something that doesn't change. Of course, because taking away 2 hydrogen ions will give you taking away hydrogen ions will produce you water molecules, but you get per reaction, you get another hydrogen atom from the NADH. So if you combine them together, then this conservation law also makes sense. You can check these individually, and you can see we find by taking this null function that there are 4 such combinations that make sense, and we'll see later about how in larger networks these conservation laws are actually quite useful information. We can also look at the other thing that we could do, namely, rather than looking at this null space of the reaction matrix, we look at the null space of the stoichiometry matrix. You remember this gives us different information. If there was something in it, we would get the so-called T invariance. However, in our primitive one reaction, there is no such thing as a T invariance. So the output is empty matrix, means no set of reactions will preserve the number of molecules if taken together. So we'll have a look at this in a while when we have a set of more than one reactions. Okay, this concludes our second exercise. We have now seen how to set up matrices, and we have gone a little bit into this formalism. What we get out of it is a way of setting up vectors and matrices from a given assumed or known mechanism, so from our biological textbook knowledge, which was summarized in this graph here. So the reaction that we knew is going to happen in the presence of peroxidase. We have been able to get things like the S matrix and the S matrix and use them for our model simulations, previously the rate of change per time unit, and now to look at important invariant features, which we can then also use when we have very large networks. Okay, so we clear everything, clear the workspace, clear the screen. And what we are going to look at next is best shown in this example. So we take this from the materials. We have a set of things happening at the same time, and we want to be able to describe these things in a Petri Net formalism. So what can we do? What we can do is the following. We think of it as a network, similar to what we did when we set up our biograph networks. In contrast to the biograph, we don't stop by setting up the network, but we now include the interactions explicitly. We add the type of interaction and the amount of change caused by the interaction. So we add this explicitly because we want to be able to describe dynamics of the network. Eventually, all biology is not defined by static networks, but by dynamics happening on these networks. And we are getting to this now in this very simple example where, if you remember from the textbook, we have a certain convention of describing nodes of these networks. They are marked here by a circular symbol. So we see three nodes in that scheme, one called inactive gene, one called active gene, and the third one called protein. And we have interactions, we have reactions that take place, or conversions that take place between these nodes, symbolized by rectangles. And they are labeled mu for a reaction from active gene to inactive gene, lambda for a reaction from inactive gene to active gene, V for a reaction from active gene or conversion from active gene to protein. It's actually a complex set of happenings going on here. And finally, a reaction denominated delta, which is supposed to have to incorporate a degradation of this protein. So 4 types of interactions taking place involving different nodes. And you remember we need to set up the input and output matrices correctly following this convention here by looking at what is our reactants, what are our products, and what happens to each species. So the species are labeled in this first line up here under each of the individual reactions. So our matrix is formed up by species times reactions. So it's a 3x4 matrix here, and this is what we need to fill in. I put this on the right side of the screen to be able to look at this while we're setting this up. And I set up my Matlab screen such that we can see them both together. So let's now we have a clear memory working memory so we don't mess things up. And let's define our input matrix. So Rob, what would you guess should be the entries to our input matrix? I start with putting square brackets. And we start by following the convention showing here. So we start by looking at the reaction lambda.
Okay, so in our input matrix, we should have, I guess, the species going into those reactions. So first of all, I guess we've got reaction lambda first. So we've got this list of 3 species, so inactive, active, and then protein. So we can see that we have 1 inactive going into reaction lambda, but none of the active gene or none of the protein.
Exactly. How would this look in my first row? So my first row, the first reaction inputs would be?
So in that order, 1, 0, 0.
1, 0, 0 in this order. And I end this with a semicolon because then we can look at the second reaction.
So the second reaction mu, it's the one on the left of the screen. So that's got an input from just the active gene and nothing else. So that would look like 0, 1, 0.
No protein. So I put another semicolon. Third reaction.
So
V.
So we've got 1 input from the active gene and nothing from anything else. So the same again, 0, 1, 0.
0, 1, 0. And that leaves us with the fourth reaction.
So delta, that's only got input from the protein, so 0, 0, 1.
We have nothing from the genes, but 1 from the protein. So that completes our reactants, and that will be our input matrix. Okay, so let's do the output matrix.
Okay.
Type output. Output equal to what? So I have this thing again. And
okay.
We start with reaction number 1. What do we get from reaction number 1?
So that's lambda again. So that is 1 output onto the active gene. So 0, 1, 0.
No protein. Semicolon.
So the next reaction is mu, and that only has output to the inactive gene. So that's 1, 0, 0.
Inactive gene, no active gene, no protein resulting, yes.
Now the third reaction, so that's the one that outputs to the protein, but it also outputs to the active gene again. So this one's different. So we've got no inactive, so 0, but then we've got 1, 1.
We can get a protein, which is the last number 1, but we also recover the active gene. So that basically symbolizes that there's no reaction where an active gene is lost and a protein is formed. You know that this can be used to be transcribed again. So we actually just recover the active gene after the protein is formed, being ready to be able to produce new protein via RNA polymerase. Right? So this was our third reaction. So we need one more reaction. What products do we get from our final reaction delta?
So there are no products. So this is the one that's leading out of protein, but it's not going anywhere. So it's 0, 0, 0.
Right. So we get none of these species that we consider here. Maybe we get something, right? We get some degradation products, or the protein just diffuses to another compartment, but we're not considering it. So this is shown in the scheme by not having an output of this delta. And it just means we're not looking at it. It doesn't mean there is nothing. It means we're not considering it. Because now we have our matrix completed and we have our output matrix. And hopefully it's the right one. We'll see in a second whether it's actually correct. So what do we do next? Now we remember how to create our reaction matrix. Our reaction matrix was A. We just do it the same way as we did before. We subtract the input from the output. So the matrix that's formed by the reactants is subtracted from the matrix formed by the products. So we have output minus input, and here it is. So we get our A matrix, and you see there's a couple of minuses there, a couple of plus ones, there and a couple of zeros there where nothing, no contribution is seen.
I guess the interesting one there is where the third reaction took in active gene and then gave out active gene as well. So that is 0. So that's the third row in the second column. Was both 1 in the input and output matrices and is now 0 in this matrix A.
Right. Which means it's similar to a catalytic particle, if you like. It participates, but it's actually recovered. It's not modified during this process, but it remains what it is. So in total, it gives us a 0, 1 minus 1 equal to 0. Yes, good observation. And we'll now immediately, of course, we know how to formulate our stoichiometry matrix. We get this from the transpose of A. And here it is. So if we get this up a little bit to look only at our matrices A and S, that's what they look like. The first one is 3 by 4, the second one is 4 by 3. And you know that the 4 comes from the 4 reactions and the 3 comes from the 3 species that we looked at. So now we can look at these invariant features. Right now we have something that's slightly more interesting than a single reaction. Why would we do that? What is the aim of looking at this null space, Rob? How do you see that as a mathematician?
Well, we were talking about this before the session, and actually a null space it's somewhat hard to explain because it does end up getting into quite a lot of mathematical terminology quite quickly. Very simply, the idea of a null space, it's those things that are invariant don't change through some sort of applying something. So in here we're interested in applying the reaction, the whole set of reactions at one time and seeing what doesn't change in total.
Right. I think that's a good point for me, because for me as a biochemist, I look from it, of course, from a different perspective. But what I'm interested in a reaction network is, well, two things that we're looking at here. There's, of course, many more things that you could do, but I'm looking at steady state. So I want to see if under open conditions, like any in vivo processes, what will be the level of molecules, the number of molecules or the concentration of molecules that is maintained by a certain reaction network. Is there such a thing as a steady state? So this is the one thing that I can measure, and where I will say this is a certain concentration that I want to predict to be found experimentally. So this is where I think computation comes in handy and useful. I can make a prediction. So we can get these from such invariants. So having formulated our system as a matrix then allows us to go back and get features like a steady state, certain reactions that actually balance each other such that a stable concentration is maintained, although there are multiple inputs and outputs. So it's a balanced type of a harmonic situation where overall there's no net change, although there's a flux through the system. So we do have synthesis, or we do have metabolic processes or signaling processes going on, but we know one feature that is being able to maintain fluxes. The second thing that we want to know, whether there are certain combinations of particles that don't change. If there's anything that I can just ignore calculating explicitly with the simulation, is there anything that I can know once I know the overall quantity? And we are always thinking of combinations like ATP plus ADP, potentially plus AMP, if that's a conserved thing. Together we have had the example of NADH and NAD plus. So if we have NAD plus NAD plus NADH, is that a conserved amount? Then we can look for this. And the purpose here is not so much to know how much there is, but to be able to reduce the complexity of our network. Because any such invariant things that don't change, we don't need to simulate them explicitly.
I think one of the issues in trying to explain this as a mathematician is invariants are things that mathematicians are really interested in. So they come up in all sorts of areas. And so when that happens, you end up getting very mathematical syntax. But what Gerald was saying is true. This is very useful in this sense as well.
So we'll see how this works in our example. Just switch our video off and we concentrate on our screen again. So we get our invariants. Now we need to remember which is which. So let's look at maybe conserved species first. Is there a way of species conservation here? And let's pretend we don't know. Of course, we might also know, but in general, in a big network, we don't know this. And conserved species, we look at what we just said, combinations like NADH plus NAD, or in this case, we want to know whether inactive, active gene and protein, whether there's any combination that is conserved. So we look at the null space of this reaction matrix. So the species conservation or conserved moieties is called the P invariant from a very different context, non-biochemical context. Conserved species, we get this from looking at the null space of the reaction matrix. So we do this, and it turns out we get a single column telling us there's one conservation, and this conservation, if we remember, the 1, 2, 3 species go in the following direction. We have reactant inactive gene is the first one, then the active gene is the second one, the third one is the protein. So what this tells us is if we add up the number of particles of the number of inactive genes plus the number of active genes, if we add these two numbers up, then this sum is a conserved entity. So it means this number will not change if we have this Petri net running changes as we have defined them before, means these 4 reactions taking place. And this is clear, of course, because what happens when we look at the original scheme is that inactive gene is by reaction lambda converted into active gene and by reaction mu converted back into inactive gene. So of course, if those 2 reactions take place, the number will always change by 1 in each of it, but we lose 1 and we always get the same thing back. So overall, these 2 taken together, the number will not change. Whatever the initial number of each is, the sum of the 2 will remain constant. So we actually only need to simulate 1. If we have a large network, there's a simplification already. Now let's look at the other thing. I use the same line from the command history. It's the null space of the stoichiometry matrix. And that was supposed to give us the so-called T invariance, which for us means what reactions taken together will leave the amount of particles unchanged. So if we assume we have some certain concentration, certain numbers of active and inactive genes and proteins, what combination of reactions will leave these numbers unchanged? So you can see, if you take all reactions together, unchanged means we have a steady state. Means everything happens, but nothing changes. Overall, we have a steady state. If we look into the individuals, individual subsets that contribute to this steady state, they are called elementary fluxes. So if you come across this technical term, elementary flux, this is what we're getting here from this null space of the stoichiometry matrix. And if we execute this function, null of S, then we see we have 2 columns, and this tells us there are 2 T invariants. There are 2 combinations of reactions that leave particle numbers unchanged, and so we need to look at them. The first thing is reaction 1 and reaction 2. So we need to go back to our original scheme to remember what it is. It's reaction lambda and mu. So this is the set of 2 reactions that interconvert the 2 types of gene species that we have, which is clear because if they both take place at the same time, we have no overall change. Inactive change is put to active change, but is also recovered at the same time. So these 2 reactions together leave. Of course, they don't touch the protein, so the protein will also be left unchanged. And we can see that this is a perfectly reasonable invariant, the so-called one of the first T invariant of this model. The second has to do with reactions that deal with the protein, and it's the reactions 3 and 4. It's the reactions V and delta, those that produce and those that degradate protein. And what this tells us that if reaction V runs and reaction delta runs at the same time, then a molecule of protein is being produced and a molecule of protein is going to be synthesized. The same amount is going to be synthesized and degraded. So overall, there's no net change in the level of protein, forming now our second conserved set of reactions that leave the concentrations unchanged, our T invariant. Okay, so we have completed this set of tasks that you're also supposed to do for the assignment. And as a final thing, now that we have looked into these more abstract things, let's have a look at what the matrices look like. So we can do this by using a command called image_sc. This is actually comes from a function which is called image, which creates an image from a matrix. If you have any matrix, you can look at the matrix using image. And if you use this variant with SC at the end, this means scale matrix. It means it assigns reasonable values to the colors. And so you are independent of what the actual entries to the matrix are. So it will scale them automatically such that matrix colors are reasonable. So let's look at, say, the stoichiometry matrix. We get a picture where we can see that we have 1, 2, 3, 4 columns and we have 3 rows, and it makes the entries of the matrix easier to see if we put in the color bar to the right. So what this tells us that the reddish brown shade is +1, the dark blue shade is -1, and the green space is telling us that there's a 0 entry, so nothing is happening. So pluses. You remember how we came up with the pluses in the stoichiometry matrix, the -1 meaning something being consumed, +1 meaning something being produced. And you can immediately see the block of inactive gene and active gene, which is on the left upper corner, formed by blue and brown, which are the 2 genes interacting. And you can see the protein reactions on the bottom right corner of this matrix. So I have an intuitive way of looking at the information that's summarized in your matrices, and you'll probably not be surprised to now see that the A matrix is the same picture turned around. So if I make this big for you, you will understand immediately where reactions are. It's now in the rows that are 4 reactions, and the 3, no, what is it, 1, 2, 3, it's reactions in the columns, 1, 2, 3, 4, and species in the rows. Right, so we have been looking at this formalism. We try to keep it simple. If you want to look at how this then turns into an actual quantitative model where you make prediction about what's happening over time, please take a look at one of the articles provided, the introductory article, where the whole formalism using actually quantitative numbers for how fast reactions go on relative to each other. It's for download in the materials section of your GoToTraining control panel. And we come to the end of our session. Today's session. Rob, are there any things that we can address in the remaining few minutes that came in from the forum?
And no questions at all today.
No questions at all. So it means you've all been busy, possibly trying to reproduce things. We'll put the video of this session up for further look down on YouTube, and there will be a link on the webpage. And I think if nothing else, we can close down. Let us advertise that we're going to have a set of 3 sessions for the very important next 3 sessions that you're going to look at, which deal mathematically with function and calculus, and from a biological perspective, which deal with actually setting up, simulating, and analyzing dynamical models in terms of differential equations. So we're going to do the real stuff, but we need to have a couple of concepts from mathematics like functions, some concepts from calculus, not too many though, but a little bit of formal background before we can actually make use of it in the terms of a biochemical or biological or physiological model. We'll have a set of examples taken from literature. And so we hope you can join us for a web session if you have difficulties with these materials. Remember to use the forums for posting questions. A large number of people are doing this, and particularly when you feel frustrated, you can just shoot it off on the forum also and let us know what's going on. Sometimes there's help from unexpected sites, and don't let it disappoint you. It's quite worth it, because after a bit of getting used to it and being able to write the code to simulate this, you will be very quickly be able to apply it to your own research. Right, 5 o'clock, we are done. Thank you very much for joining. See us in 2 weeks. You should get the link to register for the sessions. Good luck with working with the materials, and goodbye from London.
Bye.